In this video, I'll be talking about our notes on composite shapes, sectors, and arc length. So we're going to start with composite shapes. Now, composite shapes are just a shape that is made up of two or more regular shapes, like a triangle, a rectangle, or a circle. So we are going to be finding the composite area and some shaded areas. So I'm going to start with these two shapes, and you have your formulas above. We've got our area of a triangle is 1/2 base times height. We've got our area of a rectangle is length times width, and an area of a circle is pi r squared. So we'll use those to help us find the whole area of these pictures. So in my first one, I can see I've got a triangle and a rectangle. If I want the composite area, I want all of that shaded region, I need to first find the area of the triangle, the area of the rectangle, and put them together. So if you want to try these two, feel free to pause the video and press play when you're ready to check. The base of my triangle here would be this length right here. It's the bottom of my triangle. And so we can see that that is going to be across from the side 10 in this rectangle. So therefore my base is 10. And then we can see that the height is 3. And the height in a triangle has to be perpendicular to the base. And we can see that was given as perpendicular. So knowing that, we've got our formula for area of a triangle, 1/2 times base times height. So we've got 1/2 times 10 times 3. So half of 30 gets us 15. So we're left with 15 meters squared. We're talking about area, so this is square meters. And then we have our area of a rectangle. Our length was 10 meters and our width was 6 meters. So the area of that is just 10 times 6, and we end up with 60 meters squared. So separately, we've got a total of 15 meters squared up here for our whole triangle and 60 meters squared for this whole rectangle. Composite area comes from just adding those two together. So we'll be left with 75 meters squared for our composite area of that shape. In the second one, it's similar. However, we'll notice that this segment right here, that's 10 meters, is perpendicular to this. That means that this side that we don't know is actually the base that we want, and that makes 10 our height. Well, to find that base, we're going to have to consider, well, this is a right triangle. I know that this side is worth 26, so if I draw that out over here, 26 is my hypotenuse, 10 is one of my legs, and I want to find B, the base of that triangle up top, which is really a leg in that right triangle. So we can use Pythagorean theorem in order to calculate that. So a squared plus b squared equals c squared. And in our case, we have 10 squared plus b squared equals 26 squared. When we subtract, we're left with 576. And when we take the square root, we're left with b equals 24. So that tells me that my base here of my triangle is 24. I know this is the base because it is perpendicular to this height, and my height was 10. So from there, I can now calculate, well, the area of this triangle would just be 1/2 times 24 times 10, leaving me with an area of 120 meters squared for my triangle. And for my rectangle, I have a length of 26 and a width of 14. Length times width is our area of a rectangle, so 26 times 14 gets us 364 meters squared. So to complete our composite area problem, we are going to add those two shapes areas together. So 120 plus 364 to get a total of 484 meters squared for this composite shape. Now in our second two examples, these are not composite shapes, they are just the shaded region of a shape. And we can see that we've got some shapes inside of these two circles. So in my first example, I'm given a circle. I can see that there's a diameter because I have a segment that is going all the way across the circle through the center. I can also see that I have 3 radiuses coming into play here. I have one here, and one here. So if all of those are a radius, they must all equal the same amount because a radius will be the same in all cases. So I could call that x, x, and x. They're all going to be worth the same because they're all the radius of the same circle. And then I have that this chord is 5. Well, what I can see here is that if this is perpendicular to this diameter, well, then this must also be perpendicular. What I can also tell is that because this is a diameter, this inscribed angle is worth 90 degrees because an inscribed angle is always half of the arc that it intercepts. This arc would be 180 because it's a semicircle, and therefore that angle up top inside is 90 degrees. And because I have this length of 5 and two sides that are the same, that means that this angle must be congruent to this angle. We have a 45, 45, 90 triangle coming into play here because of that 90 degree angle that was up top, and these two have to be congruent, and I already have that this is 90. So I've got a 45, 45, 90 triangle working in my favor here. So because I have that and I want to find that radius x, I'm going to set up a proportion using my unit right triangle of 45, 45, 90. We learned that when that has legs of 1 and 1, you would use Pythagorean theorem to get the hypotenuse and get root 2. So we can set up a proportion to solve for this actual value. So I want x, and I can put it over 5. That's a leg over a hypotenuse. I'm comparing that to this leg of 1 over this hypotenuse of root 2. I'm going to cross multiply to solve for x, so I'm left with root 2 times x equals 5. And to get x by itself, I'm going to have 5 over root 2. Well, we've talked about how we cannot leave that that radical in the denominator, so we need to rationalize the denominator. By doing that, we multiply root 2 over itself to clear out the radical in the denominator, and we're left with 5 root 2 over 2. Therefore, my x value, or my radius, because we had said that that was all the segments right here, is equal to 5 root 2 over 2. So when we go ahead and start actually solving here for this shaded region, I'm going to first find the area of the entire circle, and I just calculated that my radius, or my x value, was 5 root 2 over 2. So now that I know that, I can plug it into the area of a circle. Pi is represented as 3.14. We're going to just abbreviate it like that. And then r is our 5 root 2 over 2. And I'm squaring this entire fraction. So when I need to square everything in there, I'm going to individually square each of those numbers. So I have 5 squared times root 2 squared, which is just 2, all over 2 squared, which is 4. So I have 25 times 2 divided by 4, 50 over 4, 12 and a half, and 12 and a half times pi leaves us with about 39 and 25 hundredths. We're measuring in inches, and this is area, so the area of my entire circle is 39 and 25 hundredths. However, I then want to take away that triangle because that part's not shaded. That means I need to calculate the area of the triangle and take it away from the area of the circle. The base of my triangle here is this x plus this x, so 2 of my x's. So if I multiply my x by 2, I'm going to essentially be canceling out that denominator of 2. And so I'll be left with a base of 5 root 2 because I had 2 times 5 root 2 over 2. So I'm just multiplying by 2. Those bases, or those 2's cancel. My height is just one of my x's though, so that is 5 root 2 over 2. Plugging that into our area of a triangle formula, we're left with 1/2 times my base of 5 root 2 times my height of 5 root 2 over 2. If it helps you put this 5 root 2 over 1 to remind yourself that it can still be in a fraction, that might help with the multiplying here. Now we're left with 5 times 5, which is 25. Root 2 times root 2 is the square root of 4, which is 2. So we're left with 25 times 2, or 50, on top. And in the denominator, we have 2 times 1 times 2, which is just 4. We'll divide by 4, and we're left with an area of 12.5 inches squared. So now, in order to get my shaded region, I'm going to take the entire circle, 39 and 25 hundredths, minus the area of my triangle, which was 12.5, and I'm left with a total of 26 and 75 hundredths inches squared. In my second circle example, I'm given a large circle and a small circle, and they both have these tick marks right here for 17 centimeters. So that means the radius of my small circle is 17 centimeters. And what I'm going to do is calculate that small circle area. So pi times my radius squared, which is 17 squared. So the area of that small circle is about 907 and 46 hundredths centimeters squared. The area of my large circle, well, now the radius of the large circle is 17 plus 17, so a total of 34. So the area will be pi times 34 squared, leaving us with approximately 3,629.84 centimeters squared. And once I have that, to find this shaded region, I'm first going to take the whole circle, 3629.84, and subtract the small circle. And when I do that, I'll kind of be left with this like donut amount of area. So we'll take out the small circle, like we're taking out the middle of a donut, and we'd be left with 2,722.38. But then what we can see is that this yellow segment of our circle right here was half of the circle because that arc was measuring 180. Therefore, I don't want the whole donut's worth of area. I only want half the donut. So I'm just going to divide that donut area by 2. And that'll leave me with that yellow shaded area for approximately 1,361 and 1900 centimeters squared. So now we're going to look at other shaded parts of our circles where it's not necessarily shapes within shapes. Now we're going to be looking at when we have something called a sector. A sector of a circle will be the region that is bounded by 2 radii of a circle and their intercepted arc. So it's this yellow region in my picture. So I would say that if I wanted just that area, well, it's only that part of the circle's area. It's not the entire area of the circle, but it's not quite a triangle either. If it was a triangle, this line would be straight and we'd have this chord AB there. But we don't have that. We have that rounded part. So we're really going to be finding a fraction of our area. It's not the whole area, but we can find a percent of it. And so we're going to use proportions in order to solve this. So we're going to set up, well, theta, and that would be the measure of the angle that is here, that amount of the circle divided by the whole circle. So your theta, your degree that you know, out of the entire circle, would be equal to the area that you want that is formed by that angle over pi r squared. Well, remember, that's just the area of the circle. So you're putting a fraction or a proportion that says this angle out of the whole angle of 360 equals the area of what you want out of the area of the whole circle. So you're setting those two fractions equal in that proportion, and we can use that to solve for our shaded area. So I'm going to apply this in these two examples. In the first one, it says find the area of the shaded sector. So we can see that the 135 degrees is actually going with the white part of our circle, and so that is a sector on its own, but we want this gray sector here. So my theta in this case is not 135, but it's the whole circle minus 135. So my theta is actually worth 225 degrees here. So what I'm going to do is plug it into this formula and say, well, I want the region of the circle that is 225 degrees worth. Out of the whole circle of 360, I want that area, so x is what I want, the area of the sector, and the area of the circle, well, it wasn't given to me, but I can find it using the formula, and I can say, well, that is just pi times the radius, which is 5, squared. That's my formula for the area of a circle. That's just going to be a value that we can get by using the calculator, but this is how we're plugging that in. So now we only have one variable to solve for. In order to solve a proportion, remember we just cross multiply. So I would have 225 times that pi times 5 squared and 360 times x. So we get this equation. And what we're going to do is try to get x by itself. So in order to do that, we just divide by 360 on both sides. And we'll be left with our x value. And in this case, it is 49.1 centimeters squared. We're talking about the area. So that 49.1 centimeters squared would just be the area of this gray section. If you wanted the area of the white section, you would just replace your theta with 135 rather than the 225, because then you want the proportion of the circle that is only worth 135 degrees of it. So in the second example, it says find the area of the circle M. So I don't necessarily want the area of a shaded part this time, but I want the area of the whole circle. And what was actually given to me is the area of the blue shaded sector. So I can see that I know that the area of one of my sectors, well, the sector was worth 165 out of the full 360. And I know that the area of the 165 sector was 38.51. So I'm going to put that out of the whole area of the circle. Well, I don't know it, so I'm going to call it x. X will be the area of our circle, and I'm just replacing this entire formula, pi r squared, with x because I want to know, well, what is the area of my circle? So I can just then cross multiply to get my x. So 165x will equal 13,863 and 6/10. We'll divide by 165 on each side, and we're left with x equals about 84 and 0/10 meters squared for our area. Now notice that looks like it's a little bit more than double the blue shaded area, which it should be because 165 is almost half the circle, but not quite. So it should be a little bit more than twice that blue area. Now in this last sector example, it says find the area of the sectors formed by the angle UTV. UTV is this central angle right here, and we can see that it's forming this small red sector and a larger blue sector. They want both in this problem. And we're also asked to leave our answer in terms of pi. So instead of rounding to the nearest tenth as we did above, we are actually going to leave this with the pi symbol. So for this small sector, I'm saying, well, my theta there is only 40 degrees out of the full circle of 360. And I want to know what's the area of the 40-degree sector, knowing that my whole area would come from taking pi times my radius of 9 squared. And from there, I'm going to cross multiply. But this time, since I'm leaving it in terms of pi, I want to look for some factors that are going to help me. So I'm just going to write out all these numbers. 40 times pi times 9 squared means 9 times 9. And now to solve this, we're going to still divide by 360 on both sides, but when I do this, I'm going to be really careful about how I write it, because instead of just writing divide by 360, I know some factors of 360 would be 40 times 9, because 40 times 9 is 360. So by breaking it up into those factors, I'm still doing what I need to do, but I'm actually saving myself some work in the calculator, because now I can say, well, 40 divided by 40 is 1 whole, 9 divided by 9 is 1 whole, we're left with 1 in the denominator, so x just equals pi times 9, or 9 pi. So right away, we've figured out that the small sector area is worth 9 pi. If you were asked to write it in terms of a decimal, you would then multiply by 3.14 and round to the nearest tenth. But in this case, we're just going to leave it like this because this is in terms of pi. Now to find the large sector area, you could repeat this and replace your 40 degrees with your difference of 360. Another option would be to find the area of the whole circle. So pi r squared would just be pi times 9 squared. So the area would be 81 pi. And I'm just going to leave it like that. That's for the whole circle. So if I know the whole circle and I know the small area, to find the large circle, I would just take my whole area of the circle minus the small sector, and that difference is 72 pi, meaning the large sector's area would be 72 pi. The last thing that we're looking at here is our arc length. Now we've talked about arc measure and we've measured in degrees, and we talked about how the central angle is always equal to the measure of the arc. But when we're actually talking about the length of an arc, we can measure it. It's a curve, so we can't just take a straight ruler to it. We're taking a part of the circumference. So we're really doing a ratio of the circumference. So very similar to above, we're going to take our theta of our sector, so say this is worth theta, and we're going to put that out of the total 360. And I'm setting that equal to the arc length, so the measure of AB, would be over 2 pi r. But 2 pi r is just the formula for the circumference of a circle. So it's just like how I did theta over 360 equals sector of the area over the whole area. Now I'm saying theta over 360 is the arc length over the whole circumference. So it's just writing a proportion in order to solve this. So in my first one, I'm asked to leave it in terms of pi. We're going to put our theta, and in this case is 120 because I want the arc length of AB. And I'm putting that out of the whole circle, 360, and saying, well, AB, let's just name it x, would be the arc length out of the entire circumference. Well, my circumference would come from doing 2 times pi times my radius, which is 2. So again, we're writing this in terms of pi, so I'm not even going to multiply these out. I'm just going to write out all these factors. 120 times 2 times pi times 2 equals 360 times x. To get x, we just divide by 360. But again, I'm going to be smart here and break up that 360 into different factors that are going to help me. Well, 360 can be 120 times 3. That's the same thing as dividing by 360. And that 120 is going to help us say, well, that's just one whole, putting it over itself. Multiply out the rest of the factors that couldn't be eliminated there, and we're left with 4 pi over 3 equals x. So that means that my length of x there would be 4 pi over 3, and it would be feet because it's the measure of our arc length, which is distance. So we would say 4 pi over 3 feet. In my next one, I will be rounding to the tenths, so we can use our calculator here. And we have our theta given to us as 40 degrees out of the total 360. And then this 4.19 inches is just the measure of this specific arc length that was related to the theta of 40. So I'm going to put that up top and say, well, I need to solve for the circumference. The circumference is the bottom of this proportion. So since I just want circumference, let's call it x. And we'll replace that whole formula with just an x in order to solve that. We can cross multiply, so 40x will equal 1508 and 4/10. Just divide by 40 on each side, and let's round to the nearest tenth, so we're left with x equals 37.7 inches squared. Or sorry, not inches squared, inches. This is circumference. We're measuring distance, so just inches, my bad. And last but not least, we are asked to find the arc length of the arc BC and the arc BDC, given the length of the diameter is 20 centimeters. So if our diameter is 20 centimeters, that makes our radius 10 centimeters. And I'm going to first start by finding my arc length of BC. So in order to do that, I'm going to use that theta of 74 degrees and set that on top of 360 degrees and say, well, I want the arc length BC, and that's going to be all out of my entire circumference, which is 2 times pi times 10. So we're going to multiply all this out. That leaves us with 360 times the arc length of BC equals 4,647.2. We'll divide by 360 on each side, so the arc length of BC is equal to about 12.9 centimeters. And again, this is arc length. We're talking about the distance, so we just put centimeters there. So now in order to find my arc BDC, I could replace the 74 with the difference of 360 and 74 and then just solve a new proportion. Or we can find the whole circumference, which is what I'm going to do here. Circumference comes from 2 pi r, so 2 times pi times 10. My circumference is about 62 and 8/10 centimeters. So in order to find this red part of my circle, I'll take my entire circumference. To get this BDC arc, I'm going to take the whole circumference, 62 and 8/10, and subtract the little arc BC that we just calculated, 12.9, and the difference there becomes our arc measure for BDC, which is 49 and 9/10 centimeters.